Hello and welcome to Lecture 8, in which we talk about floating point math and the numeric types. This is the lecture you'll watch for February 20th, 2014, CIST 1400. The reading assignment for today is effectively section 3.9 of the title text, though I'm more than happy to say that I'm more than disappointed to say really the text treatment of floating point numbers is remarkably inadequate. They kind of crammed that information into an unrelated section of an unrelated chapter, and really it's a little bit more important than that. So we're going to talk in brief today about that. Our agenda for the day. We'll talk about the numeric types. We'll talk about floating point math. We'll talk about the double type, which is the default floating point type. Then we'll talk about how to convert between the numeric types. So when we're creating variables with which to store data, there are some things that we have to consider. We need to consider what type of information we've got. Is it a number? Is it text? Is it something else? Is it something more complicated than perhaps that? We need to consider what we want to do with our data. So is this a social security number where we're probably not going to do math to it? Is it an ISBN where we check validity by doing math to it? Is it something else? We want to know if we have to worry at all about memory, which is to say if running out of memory is actually a concern. None of the programs that we write in this course this semester are ever going to be in any danger of running out of memory, assuming you write them correctly. But when we're talking very large database programs, when we're talking programs that handle millions and millions and millions of pieces of information every second, memory is a huge concern. And we also, these are things that are answered in this course, but we also have to worry about, like, where do we get the information, where do we put it, how secure does it need to be, how permanent does it need to be, who is able to access it, how they're able to access it, who shouldn't be able to access it, how we might keep them from doing so, and certainly things like internal and both internal representation of this information and also how and where we store it. Today, very specifically, we're going to talk about the numeric types, that is to say numbers, which generally fall into two categories. You have your integer types, that's your byte, your short, your int, and your long, and then the floating point numbers, which are float and double, which stands for double precision floating point number. So with integers, we can only use them to represent whole numbers. We store them in binary, and then we use them in integer arithmetic to produce more whole numbers. That is to say, 7 plus 3 is 10, 7 divided by 3 is 2. And then in general with integers, we're unable to represent decimals or fractions without doing a lot of work. There are a couple of ways that we can make it happen, but in general, it's really, really difficult to do that. Floating point numbers, we call it a floating point number because the decimal point floats, are usually used to represent decimals and fractions, and sometimes whole numbers, but mostly decimals and fractions. They're represented internally in binary, where you have some significand times 10 to some exponent. And floating point numbers, when we do them with arithmetic, we produce other floating point numbers. So if you do something like 7 divided by 3, you'll get 2.333333. There'll actually be 2 followed by 14 threes. But floating point numbers are prone to some strange rounding errors. When I say strange, what I actually just mean is unreliable. Fundamentally, though, integers and floating point numbers are different ways to represent numbers. And they're both structured in binary, but the way that the Java virtual machine interprets that binary is very, very, very different. And I want to show you real fast what it looks like. So with integers, the first bit is the sign, and then every bit after that collectively forms your number. The int, for example, is a 32-bit integer, and so you have your very first bit is the sign, positive or negative, and then the next 31 bits are the number itself, which is why, incidentally, the maximum that we can represent is 2 to the 31st. So let's start with a really, really simple integer as represented in binary. When we break this down, the very first thing that we're going to talk about, that bit in purple, that's the sign. If there's a 1, it means the number is positive. If there's 0, the number is negative. And these aren't things that you need to know for the exam, but it is useful to know at least some amount of how this works. And then everything after that is the number itself. And so with binary, this is a thing that you might have to look up if you want to really spend time with it. The easiest way to handle it is to go from right to left. So going from right to left, so this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. Okay? So what that means is that we have a 1, that's 2 to the first, a 2, 2 to the 0th, sorry, a 2, 2 to the first, a 0, but if this were a 1 we would have a 4, an 8, 2 to the third, a 16, 2 to the fourth, and a 32, 2 to the fifth, and then nothing for 2 to the sixth, though if we did that would be 64. And we add all that together and we get a 59. And since there's a 1 here in this very first bit, we know that we have a positive 59. Floating point numbers are represented using scientific notation. And this is, I'm going to show you a really simple, an overly simplified version of how this works. So the first bit is still the sign. The next couple of bits are the significand. That's the number that we're multiplying by some exponent of 10. And then the last several bits are that exponent of 10. So here's a really simple floating point number. We've got this 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1. Okay? So the part in blue, right over here, is the sign of the significand. That's the base. So it indicates that we have a negative number. And the part in red, this is our number itself. So this is the number that we're going to multiply by 10 to some power. The part in green, this is the sign of our exponent. A 1 means that it's positive, a 0 means that it's negative, and the part in purple is the exponent itself. That's the number. So when you break it down, we have a 0 here, so it's negative, then 1 plus 4 plus 16, which ends up being negative 21, times a positive 10 to the power of 1 plus 2 is 3. So we have negative 21, that's the part on the left side of that bar, times 10 cubed, that's the part on the right side of the bar. So this ultimately represents negative 21,000, as the case may be. And that's if we're using a power of 10, and the actual representation of numbers internally is more complicated than that. Usually it's often powers of 2, as determined by some international standard. And so the actual variables are a lot more complex, since we also have to store a name, a type, and a location in memory. But the description that I've given here is basically correct. That said, when we're talking about integers and floating point numbers, the thing that we have to remember is that they are fundamentally different. Okay, so these are the numeric types. Okay. Going from smallest to biggest, we have a byte, which goes from negative 128 to positive 127. This is an integer type. A short, negative 32,768 to positive 32,000, that should be 767. The int, which goes from about negative 2.1 billion to about positive 2.1 billion. The long, which goes from about negative 9 quintillion, that's a 9 followed by 18 zeros, to about positive 9 quintillion. We have a float, which goes from, which can represent somewhere between almost 0, that 1.4 to the negative 45th, to a very large number. That'll be a 3.4 followed by 37 zeros, give or take. That's accurate out to 7 digits. And then the double, which is accurate out to 15 digits. The parts in red, up here, those are your floating point types. The parts in red are those will give you things that are decimals. And the way that we can tell is because we have these decimal points here. That's one way that we can remember. The other way that we can remember is just by knowing that this is a floating point number. So we have a decimal point that moves around based on scientific notation. Or we have a double, which is the double precision floating point number. The bits in blue, those are all your integers. Those are your integer types. The one that we use by default is the int. And the floating point variety that we use by default is the double. Okay? And so with the double, it's a double precision floating point number. It's the default floating point type in Java, and we create it just like so. So double, and your variable name is equal to some value. And we can expect doubles to go out to 15 decimal places, generally. We collect doubles using the scanner's .nextDouble method. So if you have a scanner called in, we call in.nextDouble. And then we can print doubles using your regular print commands, or using printf with a %f command. A %f format sequence. With integers, it's %d for decimal integer. For floating point numbers, it's %f for floating point. And so you might have something that looks like this. And so if we do this, we'll get we'll get out pi is equal to %f pi. And I want to show you real fast a demonstration of that. So we'll take a look at this real fast. And so we're going to see a couple of things here. Create a scanner. We'll ask the user for a number. We'll collect that number as a double. We'll print the number. The %f by default goes out to 7 decimal places. We'll print the number out to 3 decimal places using the %.3f. That's a precision specifier. Then we'll print our number out to 1 decimal place using the .1f precision specifier. And I'll show you more about how to use those in a future lecture. Let's run this baby and see what happens. Okay, so it'll ask us for a number. Let's start with actually, let's start with 3.141592653. 58. Okay, so we're just going to go all the way out a little bit. When we print it out, we can see your default %f is going to give us out to 7 digits precision. Out to the nearest thousandth is 3.14, 3.142, that 5 rounds up to 2. Out to the nearest tenth, 3.1. This will let us collect doubles pretty easily. Let's say we give it an integer. Let's say we give it a 8. No 0.0 or anything, just an 8. It'll still get turned into a double through a process called promotion. We'll talk about that in a second. Where you have 8.0, a whole bunch of zeros, fewer zeros, even fewer zeros still. And so this will work with positive numbers, with negative numbers, and with certainly with 0. That's the big thing about the doubles. Like when we see this 8 here, this isn't an integer. This is a floating point number, and we can tell because there's a decimal point here. Okay, so if you look back at the slide, when we're doing arithmetic with floating point numbers, the thing that we have to remember is that when we do that, we get a floating point number as a result. So with the integer type, we might do something like 7 plus 2 is equal to 9, 7 divided by 3 is 2. With the double, 7 plus 2, those are both going to get promoted, and we'll talk about that later, is going to give you a 9.0, and 7 divided by 3 is a 2.3333333. So I want to show you real fast also what floating point math looks like. Okay, so here's what we have. We've got 2 integers, and we'll print out their sum, their difference, their product, and their quotient. And then we have those same numbers as doubles. We'll print out their sum, their difference, their product, and their quotient. Okay? These are the same numbers, just different representations. And what we see here, so 43 plus 12, 43 minus 12, 43 times 12, and 43 divided by 12. In all of these cases, we get integers out. When you print these out as floating point numbers, we still get like 55, so that matches up. 31 matches up. 516 matches up. But instead of a 3, we get a 3.58333333. Or 3 and 5/12 if we're wanting to be a little bit more specific. And so that's probably the biggest difference. And by probably, I mean that's exactly the biggest difference. When we do integers, when you do arithmetic with integers, we get integers out. When you do arithmetic with floating point numbers, we get floating point numbers out. And what we'll talk about here in a second is how to convert between some of those types. See you in a bit.